Welcome to another class of fundamentals of particle and fluid solid processing. Today we will be looking at the boundary layer, the fundamentals of boundary layer that you have already known from your fluid mechanics background. This will again serve as a refresher slides to your memory. So, I hope there would not be much difficulty in following these slides, which we will quickly go through to the basics, and then we will again see the link that why these knowledges are important in this course. So, when we talk about boundary layer, this picture immediately comes to our mind that how or what is boundary layer or how that forms. So, boundary layer we can call this as a thin layer of a moving fluid where the fluid movement is influenced by the solid boundary. We can broadly say by this definition that it is a thin layer of moving fluid attached to the surface of the solid surface where the fluid movement is influenced by the solid boundary. So, what happens in this schematic, what I have tried to show you is that let us say this hard line is a solid surface. There is an object, flat plate, let us consider the example of a flat plate, and there it is approached by a uniform fluid velocity. Okay. This approaching velocity is uniform and it is coming onto this flat plate. So, when it flows over the flat plate, what happens? Let us consider for the time being this flow is laminar and has uniform velocity. So, near to the surface, this solid fluid interface, there the velocity of this fluid is 0, and as we go far from the solid surface, there we see such kind of a velocity distribution. Okay. Now, these velocity distributions are asymptotic in nature. So, the point is that it achieves the bulk fluid velocity some point far from the solid object. Now, these points, let us say, are these imaginary these points are connected by this imaginary line. So, what happens that this imaginary line divides this flow domain into two segments basically. One where the fluid velocity is influenced or gradually changes from near surface, that is 0, to a velocity that is close to the bulk fluid velocity, or we say that as a free stream velocity, and the other region where we see that the velocity is not influenced or nearly constant or nearly not varying with the distance that is from the leading edge of the flat plate. So, what happens? This imaginary line we call as the boundary layer, and this is the thickness of the boundary layer. Okay. So, this boundary layer, which means basically bisects or not bisects, it divides this fluid flow region into two segments where velocity varies or influenced by the solid boundary, and the other portion where that is not varying or nearly in fact is constant. So, this thickness of the boundary layer, okay, that depends on the type of the body or the object that we are considering here. So, again we stick to the flat plate example. Now, here we can see the thickness of the boundary layer that we define as a from the surface of the body, as I said, to the line that passes through all points where the velocity is nearly same to the bulk velocity. Now, as I said, these velocity lines are asymptotic in nature, so it never reaches the actual velocity. So, we typically say that 99% of the fluid velocity or the bulk fluid velocity, whenever that is reached, we take those points. So, in this case, the distance from the leading edge to this point, so let us say here the velocity is profiled like this, and here at this point the velocity is the 99% of this bulk velocity or the approach velocity. There we select the point. So, similarly, from another distance from the leading edge, we find out that point, but remember these are all the imaginary points. Okay. So, when we connect these imaginary points and get this imaginary line which is designated by OL, here in this picture we can see it is in a better view. So, when that happens, this imaginary line, we say that this is the boundary layer thickness at a certain distance from the leading edge of the solid flat plate. Okay. So, this boundary layer divides this region in two segments where the velocity is constant, this is the outer region, and inside the boundary layer the velocity varies from 0 at the wall to nearly same velocity as of the free stream velocity or the bulk fluid velocity. So, what is that thickness? How do we know that how much is this distance from here surface to this boundary layer as it is varying? Okay. Or what is the overall thickness of this boundary layer when the flow gets fully developed? Now, what is fully developed? We will come to that. So, in boundary layer or within the boundary layer, there are few points that you need to remember, that the velocity at the interface or the solid fluid interface is 0. Velocity near the surface is essentially laminar. It is of very low velocity flow. So, that is why we typically consider that the velocity near that plate, irrespective of its approach velocity, is laminar. But sometimes what happens, although the fluid happens to be laminar in that layer, but sometimes eddies can form, and that eddies due to turbulence or some obstruction or some influence of the geometry that creates some eddies or wake, that alters the flow profile in that layer of the laminar flow. And then what happens, it influences the near wall average velocity profile. Okay. But it hardly changes the overall profile at the bulk velocity. Okay. So, the point is that the point I am trying to make here is that although we consider the surface near the near surface velocity is laminar, sometimes some small eddies or currents can happen there, and then some local velocity profile change can be observed or can happen, and that change or the alteration basically enhances several things or significantly alters several parameters like temperature and concentration. Okay. And sometimes that helps to have a better mixing in fluid, because in mixing we require turbulence. But far away from the surface, flow field can be turbulent, and usually if the approach velocity is so, it is definitely turbulent. So, in between this fully developed turbulent flow or the fully developed turbulent layer and the near surface laminar region, there can be several sublayers. Okay. Those are listed here, that is the viscous sublayer, buffer layer, and then we have the turbulent layer. So, in between this surface and the free stream region or inside the boundary layer, we can have viscous sublayer, buffer layer and the turbulent layer. So, buffer layer can also be considered as kind of a transition layer, because if the flow changes from laminar to turbulent, there is that buffer or the transition layer is there. So, at the leading edge of an immersed body, or let us say here the flat plate, the boundary layer is usually very thin and purely laminar. Now, this appearance of turbulence can be recognized by sudden and rapid increase in the boundary layer thickness. So, if you remember or if you realize this picture here again, or the schematic, this near the leading edge, okay, the boundary layer is typically very thin. In fact, this whole boundary layer is very thin depending on the flow scenario, and it is a mostly exaggerated picture that we show or any textbook shows. So, here typically near this leading edge, the boundary layer is very thin and it is mostly laminar in nature, but then there can be a sudden increase in the boundary layer, and that actually dictates that there is the onset of turbulence layer. So, then what happens, and after that again, as we go far from the leading edge of this flat plate, that turbulence sometimes dissipates or sometimes it is carried away by its bulk fluid velocity. So, in laminar cases, the thickness of this boundary layer typically varies with the x to the power 0.5, where x is the distance from the leading edge. Okay. So, for laminar case, thickness of the boundary layer changes with x to the power 0.5 with multiplied by certain cofactors or prefactors, and those relations are typically suggested by several researchers by their several experiments, but typically it varies by this factor. And at the onset of the turbulence, when there is a sudden change in that boundary layer thickness, the thickness changes with x to the power 1.5. It rapidly changes. These indices indicate that the rapid change of the boundary layer thickness as we go from the leading edge to the far away to its tailing end. So, for fully developed turbulence cases, this thickness then changes with x to the power 0.8. So, after the onset of the turbulence, if the turbulence prevails, then it goes in this manner or it changes in this manner. So, where again x is the distance from the leading edge to its tailing end, the length that we go from that side. Okay. So, now the point is that how the boundary layer develops. Now, this again, this concept possibly you have already seen in your previous fluid mechanics class, is that when typically this is, let us say, the uniform velocity that comes in a pipe or a conduit. Okay. When it comes in the pipe, there is the development of the boundary layer. Now, as soon as it enters, the boundary layer starts to form and its thickness grows. So, this part, let us say, the initial part of the pipe or a certain length that is required to develop the boundary layer to a fully developed region. So, what happens is that as soon as it enters, the boundary layer starts to develop, okay, and in the developing region, the fluid flows like a rod kind of a behavior, because here the fluid movement is there and here the boundary layer. So, here the flow is very low, as you can see that we can understand that in the boundary layer we have seen there is a laminar flow or the viscous sublayer, buffer layer, and then the turbulent flow or the flow of free stream region comes into play. So, there is a substantial velocity gradient, and here the bulk fluid flows in a rod like manner, and after a certain distance this boundary layer basically comes to the center of this pipe or the conduit, and then the fully developed region happens. So, here in the fully developed profile, the boundary layer basically coincides at this center plane from both the sides. So, it from this side it goes like this, and from the top it comes up like this, and it coincides at the center, and then the velocity profile gets like this. So, in fully developed flow, when the flow occurs without varying velocity distribution, we typically call such scenario as a fully developed flow, that is here. Now, this profile is then maintained irrespective of its direction in the, if we consider this as the positive x direction. Okay. So, the fully developed region, we can say that where the boundary layer coincides at the central line of the fluid, or in fact, and that is when the flow profile does not vary with its distance from the inlet to the outlet. So, from that point onward, we can say that the flow profile is now fully developed, and its flow the velocity distribution is not changing along the axial length of the pipe or the conduit. Now, quite naturally, as we say that this fully developed flow, it requires a certain length. So, that means that length is typically characterized by the transition length. The length from the entrance to the point where the boundary layer reaches the center of the pipe or the conduit, and the fully developed flow takes place. Okay. So, till this distance in a pipe, we call this is the transition length. This is the transition length that is required to have the fully developed flow. So, this length varies or depends on the flow condition. So, for laminar flow, this transition length, this xt, as I said, the distance from the inlet in a pipe, here in this case d is the diameter of the pipe or the conduit, it varies like in this manner, 0.05 of Reynolds number. Okay. So, for laminar flow, transition length required is 0.05 multiplied by Reynolds number multiplied by its diameter or inside diameter of the flow. For turbulent flow, it, or let us say typically when it goes very higher velocity, the transition and the turbulent flow occurs. So, where in the fully turbulent cases, we see that this entrance length or the transition length is nearly independent of the Reynolds number, and that transition length typically is 40 to 50 diameter of that pipe or the conduit where the boundary layer is developing. So, for example, to give you the numbers, so for a 50 millimeter ID pipe with a Reynolds number of 500, we see that the transition length by this formula, it is around 3.75 meter. Now, what we expect, or intuitively you can think that for possibly turbulent flow, this length will be much more to have the fully developed region. But the point is that in the very high velocity of the turbulent flows or fully turbulent cases, this value is around 2 to 3 meter. Why this happens? We will see in the next slides, or in fact in the other slides, that this region, this reason for this thing, why this is happening. So, there can be scenario that the flow becomes turbulent after entering the pipe. Okay. So, initially there was laminar case or some different condition of flow, but as it enters a pipe, it becomes turbulent. So, in that case, the transition length requires the length required is very higher, okay, and it is in fact in the range of 100 of the pipe diameter or the conduit diameter. Now, the point is that when boundary layer separation happens, the boundary layer separation happens. So, if for example, this flat plate, we discussed this thing that the uniform, let us say a velocity is approaching this flat plate. So, we have boundary layer development in both the sides, upper and the bottom of this flat plate, upper side and the bottom side. Now, the point is that when that happens and at the end of this flat plate, okay, there will be still some gradient in the flow, but as we go along this distance in the positive direction, we can again have uniform velocity after a certain. So, this gradient can persist till a certain point, but then again we can have the uniform velocity if the scenario is like this. But now consider this flat plate is perpendicular to the direction of the flow. So, what happens here, that this boundary layer develops at the surface, and then there is a sudden, due to this momentum of this fluid, okay, this boundary layer cannot be suddenly coming to this point and is flows with the momentum of the flow. Okay. So, in that case what happens, this back portions of this vertical plate sometimes become, or in fact becomes, as a backwater kind of a scenario, where decelerating velocities are there and the flow field occurs, and this results in a sudden drop in a pressure, or the larger pressure drop, and it creates the eddies or the wake. Okay. And this wake consumes considerable mechanical energy and result in larger pressure losses. Okay. This formation of wake happens due to this boundary layer separations, because it cannot abruptly come to this point and it flows with the momentum of the flow. In such scenario, the eddies or the wake forms, and that leads to this considerable mechanical energy loss and the pressure loss. So, this results, this boundary layer separation can be resulted from the large alteration of the velocity in the fluid, and that can be occurred by change in magnitude of the flow field, change in direction of the flow field. It can happen due to sudden expansion or constriction of the flow path, as well as the flow path can be tweaked by bend, obstruction or something like that. Okay. So, boundary layer separation is mostly undesirable due to this wake formation that results in significant pressure loss, but it is sometimes desirable in cases where we require enhanced mass transfer or mixing of fluid. Okay. So, in those cases this kind of wake formation or local turbulence, local wake formations is helpful or helps us to have the enhanced conditions. Now, at low flow rates there is no boundary layer separation. Okay. As the velocity increases, we have now understood the onset of separation happens, the onset of separation is there, and the skin friction or the wall friction that we discussed in the last class, contribution becomes lesser and lesser. Okay. At very high velocity or when there is turbulent condition, flow within the boundary layer initially shifts from streamline to turbulent cases before the separation occurs. Okay. So, this is the condition at the very high velocity or at the very high turbulence region or the fully turbulent cases. Now, once that happens, that even before the separation takes place, if the streamlines changes, the boundary layer shifts from the streamlines to the turbulent, then what happens, rate of transfer of momentum in turbulent case is much higher than the streamline conditions. So, the separation may not arise. Okay. Now, this is some interesting feature, that in laminar case, that is why we had sufficient length that was required to have the fully developed flow. But in highly turbulent cases, since the boundary layer separation is suppressed by the high rate of transfer of momentum from one point to another, quickly that fully developed length can be achieved. Okay. Now, the point is that this is an interesting point for our case, that the fundamentals of particles and the fluid solid processing, that when there is a submerged object, or let us say a sphere, and the smooth sphere, okay, and then what happens, the condition is laminar, the flow field is laminar, you can understand there will be the change in the flow field, or the boundary layer separation will happen, okay. But if you somehow can tweak the flow field, or you can induce turbulence there, okay, that can result in a reduced drag or the reduced pressure drop, because then this scenario is much more suppressed. So, how it has been done by the scientist? In fact, Prandtl did this by sticking a hoop in front of a sphere when the sphere is submerged and the flow field was coming. So, at the front end of the sphere, if you create some roughness, then that onsets the triggers the turbulence and the flow field changes, and the boundary layer and all these things gets different than the normal scenario, and the drag becomes reduced. So, magnitude of form drag is basically influenced by the shape of the object, and that is our main consideration in this study, because we will be dealing with different types of the material or the particle, and the particle shapes will be different, or the shapes will be different. So, we will see some examples of this concept, boundary layer and the drag, in the forthcoming classes. Till then, I would like you to go through this theory, and thank you for your attention.